On my poster, I'm going to show you my results about BCFT boundary deformations and how they can be related to JT gravity. The content of my poster can be well summarized in the following picture, where on the right side we have an BCFT defined in the positive Minkowski half plane, and on the left side we have an ADS2 bath system where the red shaded region is equipped with an ADS2 metric. And we compute the entanglement entropy of these both systems to provide further evidence for the conjecture that turning on a non-trivial dilaton field in the ADS2 region is equivalent to a boundary deformation of our BCFT on the right side here. The boundary will be deformed by conformal transformations, by these Möbius transformations. To be more precise, we consider the infinitesimal broken transformations, which indeed change the shape of the boundary. And we will perturb the formula for the entanglement entropy of the interval 0 to bx up to first order in the conformal parameters there. The deformation of the boundary is performed in the following steps. First, we deform the boundary by f while leaving the point B invariant, and afterwards we transform the boundary back to a straight boundary, but now move the point B with the inverse conformal transformation f. For our deformed entanglement entropy, we obtain the first result here, which is now the deformed entanglement entropy consisting of the undeformed formula and the first order term, which has the form of a dilaton profile in JT gravity, which will be commented now. So we equip the ADS2 bath system and the ADS2 region with a non-trivial dilaton field given by this expression here. And we start with the generalized entanglement entropy for the interval A to B, which consists of phi 0, a constant, the dilaton field, and the bulk entanglement entropy given by this expression here. And since the entanglement entropy of the BCFT is dual to the island entropy in the ADS bath system, we compute the island entropy by extremization. So first we consider the case of a non-trivial dilaton field, which is vanishing. So we have this parameter configuration in our dilaton solution, and we can compute extremal points of our generalized entropy, and inserting them we obtain the island entropy here. And if we compare this result with the undeformed entanglement entropy in our BCFT, we obtain the following parameter matching, where we now find an expression of the boundary entanglement entropy here in terms of the constant phi 0, L, and epsilon tilde. If we switch on the dilaton field and consider the particular case where kappa is not 0 and the other parameters are, we can again compute extremal points given by these expressions here, and we obtain the island entropy by the same procedure. And if we use the result from the previous slide and insert it, we have this simplified form for the island entropy, and we can go on and compare this result with our obtained result for our BCFT boundary deformation here, and we find the following parameter matching that kappa equals to beta, and in an analog way we find that lambda equals to alpha minus delta and mu equals to minus gamma. And we have switched on the dilaton field, and it only moves the point A to linear order or higher orders. But since the dilaton is always a linear approximation of our gravitating system, or to be more precise, JT gravity, the change in A is of second order and higher. So that's the reason why we can neglect the higher contributions. So I thank you for your attention, And I'm looking forward to see you at my poster in the conference. I would be really happy.